is a sequences and series.
A rabbit population grew in the following pattern: 2, 4, 8, and 16. If all the rabbits live and the pattern continues, how many rabbits will be in the 8th generation? Step 1 to solving the problem is you have to find the key in the sequence. The sequence is 2, 4, 8, and 16. The key to this sequence is to multiply by 2 each time. The key again is A times 2 equals B. The generations, if you were to continue to the 8th generation, would be 2, 4, 8, 16, 32, 64, 128, 256, and 512. The answer would be C, 256. We solved it our way by multiplying everything by 2 to get to the 8th generation. But if you come across a harder problem, you can use the general rule for geometric sequence to help you get your answer. A sub n equals A sub 1 r n minus 1, where n is the position of the number you are looking for. In our case, it is 8 for the 8th generation. A sub 1 is the first number in the sequence. In our case, it is 2. R is the ratio between the numbers. In our case, it is 2 because each number is multiplied by 2 to get the next number. When you substitute all the numbers, we get A sub 8 equals 2 times 2, 8 minus 1. Or A sub 8 equals 2 times 2 to the 7th power. Or A sub 8 equals 2, 128. Or A sub 8 equals 256. Which means in the 8th generation, there will be 256 rabbits. Here is an addition example we found online to help you with the general rule for a geometric sequence. I will play it for you.
Videos on the topic, but it's really a good place to start just to understand what we're talking about when someone tells you a geometric sequence. Now, a good starting point is just what is a sequence? And a sequence is, you can imagine, just a progression of numbers. So, for example, this isn't even a geometric series. If I just said, 1, comma, 2, comma, 3, comma, 4, comma, 5, this is a sequence of numbers. It's not a geometric sequence, but it is a sequence. Now, a geometric sequence is a special progression or a special sequence of numbers where each successive number is a fixed multiple of the number before it. So let me explain what I'm saying. So let's say my first number is 2, and then I multiply 2 by the number 3. So I multiply it by 3, I get 6. And then I multiply 6 times the number 3, and I get 18. And then I multiply 18 times the number 3, and I get 54. And I just keep going that way. So I just keep multiplying by the number 3. So I started, if we want to get some notation here, this is my first term. Call it A1 for my sequence. And each time I'm multiplying it by a common number. And that number is often called the common ratio. So in this case, A1 is equal to 2, and my common ratio is equal to 3. Common ratio. So if someone were to tell you, hey, you've got a geometric sequence, A1 is equal to 90, and your common ratio is equal to negative 1/3, that means that the first term of your sequence is 90. The second term is negative 1/3 times 90, which is what? That's negative 30, right? 1/3 times 90 is 30, and then put the negative number. Then the next number is going to be 1/3 times this. So 1/3, or negative 1/3 times this. 1/3 times 30 is 10. The negatives cancel out, so you get positive 10. Then the next number is going to be 10 times negative 1/3, or negative 10/3. And then the next number is going to be negative 10/3 times negative 1/3. It's going to be positive 10/3. And you can just keep going on with this sequence. So that's what people talk about when they mean a geometric sequence. And I want to make one little distinction here. This always used to confuse me because the terms are used very often in the same context. These are sequences. These are kind of a progression of numbers, 2, then 6, then 18, 90, then negative 30, then 10, then negative 10 over 3, then, oh sorry, then this is positive 10 over 9, right? Negative 1/3 times negative 10 over 3, negatives cancel out, right, 10 over 9, don't want to make a mistake here. These are sequences. You might also see the word a series. You might also see the word a series, and you might even see a geometric series. A series, the most conventional use of the word series, means a sum of a sequence. So for example, this is a geometric sequence. A geometric series would be 90 plus negative 30 plus 10 plus negative 10 over 3 plus 10 over 9. So a general way to view it is that a series is the sum of a sequence. I just want to make that clear because that used to confuse me a lot when I first learned about these things. But anyway, let's go back to the notion of a geometric sequence and actually do a word problem that deals with one of these. So they're telling us that Anne goes bungee jumping off of a bridge above water. So Anne bungee jumping. Anne is bungee jumping. On the initial jump, the cord stretches by 120 feet. So on A1, our initial jump, the cord stretches by 120 feet. We could write it this way. Let's write it this way. We could write jump, and then how much the cord stretches. So on the initial jump, on jump 1, the cord stretches 120 feet. And it says on the next bounce, the stretch is 60% of the original jump, and then each additional bounce stretches the rope 60% of the previous stretch. So here the common ratio, where each successive term in our sequence is going to be 60% of the previous term, or it's going to be 0.6 times the previous term. So on the second jump, we're going to stretch 60% of that, or 0.6 times 120, which is equal to what? That's equal to 72. Then on the third jump, we're going to stretch 0.6 of 72, or 0.6 times this. So it would be 0.6 times 0.6 times 120. And then on the fourth jump, notice over here, so on the fourth jump, we're going to have 0.6 times 0.6 times 0.6 times 120. 60% of this jump. So every time we're 60% of the previous jump. So if we want to make a general formula for this, just based on the way we've defined it right here, so the stretch on the nth jump, what would it be? So let's see, we start at 120 times 0.6 times 0.6, let me do the 0.6 here, times 0.6 to the what? To the n minus 1. Now how did I get this? Let me write this down. So this is equal to 0.6, actually let me write the 120 first. This is equal to 120 times 0.6 to the n minus 1. How did I get that? Well, we're defining the first jump as stretching 120 feet. So when you put n is equal to 1 here, you get 1 minus 1, 0. So you have 0.6 to the 0th power, so you just get a 1 here. And that's exactly what happened on the first jump. Then on the second jump, you put a 2 minus 1. And notice, 2 minus 1 is the first power, and we have exactly 1.6 here. So I figured it was n minus 1 because when n is 2, we have 1.6. When n is 3, we have 2.6's multiplied by themselves. When n is 4, we have 0.6 to the third power. So whatever n is, we're taking 0.6 to the n minus 1th power, and of course we're multiplying that times 120. Now, the question question, they also ask us, what will be the rope stretch on the 12th bounce? On the 12th bounce. And over here, I'm going to use the calculator. And actually, let me correct this a little bit. This isn't incorrect, but they're talking about the bounce. And we could call the jump the 0th bounce. So let me change that. This isn't wrong, but I want to make it a little bit more. I think this is where they're going with the problem. So you can view the initial stretch as the 0th bounce. So let me, instead of labeling it jump, let me label it bounce. So the initial stretch is the 0th bounce. Then this would be the first bounce, the second bounce, the third bounce. And then our formula becomes a lot simpler. Because if you said the stretch on nth bounce, then the formula just becomes 0.6 to the n times 120. Right? On the 0th bounce, that was our original stretch. You get 0.6 to the 0, that's 1 times 120. On the first bounce, 0.6 to the 1, 0.6 to the 1, you have 1.6 right here. 0.6 times the previous stretch, or the previous bounce. So this has it in terms of bounces, which I think is what the questioner wants us to do. So what about the 12th bounce? 12th bounce, using this convention right there. So if we do the 12th bounce, let's just get our calculator out. We're going to have 120 times 0.6 to the 12th power. And it hopefully will get order of operations, right? Because exponents take precedence over multiplication, so it'll just take 0.6 to the 12th power only. And so this is equal to 0.26 feet. So this is equal to 0.26 feet. So after your 12th bounce, she's going to be barely moving. She's going to be moving about 3 inches on that 12th bounce. Well, anyway, hopefully you found this helpful, and I apologize for the slight divergence here. But actually, I think on some level that's instructive, because you always have to make sure that your n matches well with what your results are. So when I talked about just, your first jump, I said, okay, this is 1, and then I had this 0.6 to the 0th power, so I did n minus 1. But then when I relabeled things in terms of bounces, this was the 0th bounce, then this makes sense, and this is 0.6 to the 0th power. This is the first bounce, then this would be 0.6 to the first power. Second bounce, 0.6 to the second power, and made our equation